presentations is to not talk to you as a vendor, but talk from a kind of a generic educational perspective. So I've pulled together today a presentation very much around the subject matter of kind of navigating or how to enable mobile robots effectively to kind of help with their navigation capabilities. And this has very much been put together from a point of view of kind of the struggles and the challenges we see from our customer base around the world. But with the things you see here aren't necessarily our customers, and the technology is a mixed bag of technology you'll see from our competitors and free offerings and what have you. So it's very much a very broad church in terms of content. So what I was going to kick off with, I remember the briefing, we'll go here, is really, first of all, why do we need position accuracy at all? And what we generally find in the market are there are traditional players who really understand the space when it comes to satellite, the use of satellite technology for positioning and understanding and helping with different products navigate or know where they are. But then we see lots and lots of startups around the world who are coming more from a software perspective. These are companies who are saying, wouldn't it be a great idea if we could create like a drone-based delivery service where the people are living in flat blocks, we can't have these crawl-along drones, we need these things to fly in accurately. And so someone comes up with this great idea, and then they go and buy some NVIDIA boards, or they get some bits and pieces together, and they create a drone, or they might be expert in the drone area, and then they start finding these challenges with the actual navigation piece, because they've come from a solution-solving perspective. They haven't come from a GNSS, Global Navigation Satellite Technology background, and they haven't got the experience necessarily, or the knowledge of these problems they're going to hit. So this session really is about kind of providing a bit more light on these areas that you will discover as being challenging if you haven't already. But I appreciate some of you obviously work already in this space and will know some of this stuff. So position accuracy, it's a thing we just take for granted. If I go out running with my dog, I'll turn on my Garmin Forerunner, and when I get back, if I can ever be bothered to look at it again, I can see how far I did or didn't run compared to my last race or my last run. But there, the accuracy, I'm not zooming in on that map, and I don't really care about whether, and you often see it if you're running, if you're runners, or if you're biking, you go through tunnels, your GPS computer or your watch will quite often go, hey, I've lost the GPS for a while. And you think, it doesn't matter. I'm only mapping, my run. And so eventually you'll pop out the tunnel or at some foliage, and you'll eventually get your GPS back. But again, it's only giving you an accuracy of maybe 5 to 10 meters. It's not actually recording exactly where I am, because I don't need to. My watch doesn't need to. I just need to know roughly, have I hit my 5K PB, as an example. However, when we get stuck into these types of things, lots of different companies you see in the news quite a lot around now autonomous taxis or any autonomous vehicle. If you're going to hop in one of these, you probably need to know that it's not going to be acting like my watch. And we're going to have 3 to 5 meter accuracy here or there, and we might make it to our end destination if we're lucky. These things really do need to know where they are, and satellite is part of the ingredients. It's one of the ingredients involved in very precise autonomous navigation, and that's kind of where we're headed with this. So there's different types, and U-blox as a brand, many of you know it. We kind of specialize in all this technology, ranging from what we'd call our standard precision, so kind of single or dual band based GNSS receivers, right through to high end and multi-band receivers. And the more bands and satellites you can see, the more accurate you can calculate your position. And there's lots of magic sort of happening under the hood there to enable this. And these are the types of applications that maybe some of you are kind of working on, and they're evolving in all types of areas. So typically GNSS, or this high precision satellite technology, was typically used over many years with big companies like Trimble and Hexagon, and names involved pretty much in surveying, in geodetic industries, mining, things like this, where again, you need to know to a centimetre precision, if not millimetre, where something is. You often see surveyors setting up their theodolites and all of this kind of stuff with their base stations, and they will stay in place for an entire build, because everyone knows, like a truth system, everyone knows precisely where every object is on that build site. But now in many of these types of applications, that's not possible. You can't suddenly survey the environment and set up what they call a real-time kinematic kind of base station network or reference network in the local area. You need products that you're going to ship around the world to customers that just have to be precise, or precise in terms of where they are. So again, as I say, we see all sorts of drone applications coming to market, very much in the ag space. So some of these start to mix together. Precision, weeding, all these types of crazy applications you'll find. Everything's moving into robotics, partly because of labour challenges. So in most of these areas around the world, we see that there's more skilled workforces who want to do less of the unskilled work, and therefore mobile robots are coming along to fix that kind of problem, the workforce problem, and you'll see more and more moving outdoors. And again, we've seen in Milton Keynes and places like this, delivery ground robot trials running at the moment with some vendors. So, it's coming. And sometimes you think, one day these things will be here, but you can hop in San Francisco now into a self-driving, and many cities across the US, self-driving taxis. And for a moment you might think, how does it do it? And so this is kind of a little bit around an insight into how the challenges are being overcome that are faced here. So lots of applications where we need to know where things are to a very fine degree of accuracy. And it's not just about the satellite component. And so as I mentioned, the likes of NVIDIA, no wonder their stock price is so high, simply because they have kits and boards and the capabilities for customers to start bringing in multiple sensors into this kind of product design. So typically we'll have some kind of inertial sensor which has accelerometers on board, and we can work out the velocity and the angle of something where it is, mixed maybe with LiDAR. So again, these products, these autonomous robots, if you will, or self-driving vehicles, will use a range of sensors to calculate where they are. They will never use just the one. So the navigation piece is one important factor, but then actual spatial awareness and using visual sensor input all gets pushed into effectively, in some kind of computing capability. Typically more advanced inertial sensors are coming to market from vendors. And on board some of those, you'll find maybe some of our chips from a GNSS perspective as well. But these are the types of things that effectively the developers today have to tackle. Depending on your application, is it a slow-moving vehicle? Is it a fast-moving flying object? You will use different sensor inputs, and they all have their own challenges to overcome. But one of the most challenging is the tackling of the physics behind the satellite aspect, which every time I talk to our technical teams, I always learn something, and it almost blows my brains about the world itself, about how do we overcome these challenges in the first place. So one of the areas which is not particularly well known is the fact that if I do have my high precision receiver, and it doesn't matter whose you buy in the world or whose you use, there's only so much accuracy such a satellite receiver can actually do. And because effectively you've got, geostationary satellites, 20,000, 30,000, 40,000 kilometers in the sky circling the Earth, maybe 500 to 600 of them, and you're using those to kind of help triangulate the thing is trying to use those to work out where it is to a level of accuracy that's very high in these applications we're talking around. And the challenge is, as the signals literally travel through space and down through our atmosphere, the Earth's there are physics involved to stop them getting down to a triangulated millimeter. Typically, some of the challenges are the fact that all these, the orbits and clocks of these satellites they're all moving. So we need to tell the receiver where I'll be now, and now, and now. So we need to keep that flowing into the receiver so it really does know where it is in terms of space and time. And then we have these other challenges, which is around. These are kind of the error sources, if you will, and this is the amount of error you would get. So from an advertised GNSS receiver, it might say, if you're lucky, you'll get down to a meter accuracy in the perfect condition, in the desert, outside, staring at the sky. But that's never the perfect scenario. But there's other challenges. The reason you can't get any better than a meter really is the fact that you've got, the refraction and the changes in the atmosphere are making the waves move, that they're kind of wobbling down to the surface, and they're throwing out their accuracy. So this is why, for these level of applications, these highly precise applications, we need to correct the errors happening from space. And that's where you'll hear of the term correction services, of which there's a range of these available. We provide one, and there's different ways in which they can be used and deployed, and they have huge cost implications in terms of which ones you choose. And again, when it comes to mass market robotics, where we're trying to sell lots of products, we want to stick them on Amazon and ship them to anywhere in the world, the choice of correction service is critical for this application approach for your business. And I'll come on to explain a little more around this. So you've effectively got three broad, there's other variants of how we can get correction data down to these devices, but the device typically needs to somehow receive the corrections so it can say, I think I'm here, but I'm now told I'm exactly here. And so that's the purpose of these correction services. And they come in 3 broad flavors. The traditional market has always used what they call RTK, real-time kinematic services. And this is the ones I mentioned before. The surveyors, the mining companies, these traditional players will set these up, as in you'll have a single base station set up, a reference station set up on the site. And once that's calibrated, we know where it is. So that's almost like a truth system. We know exactly where it is. So all of the other receivers that might talk to it, even though they're moving, because this one's been calibrated, we now know where the others are in terms of position accuracy. Then on the other side of the kind of the spectrum, until recently, have been what we call our PPP services, precise point position services. And again, this RTK service, by the way, is using also in most cases a cellular network as well, because what's happening here is we talk to this base system I mentioned is often a reference station actually run by an organisation. So we have to talk to the internet to receive the corrections from those reference stations and send that down to our receiver. So there's kind of quite high operational cost in some shape or form. We either have to set it all up ourselves with our own people and staff, or we subscribe to over the internet using cellular data to get this information down. The second option is not using the internet at all, and you'll hear more and more people talking about Galileo HAS, for example, which is a new arrival, free arrival from the European Space Agency, covering mostly global. It will be, but again, this is effectively beaming some of the corrections down over the actual satellite base layer as well, the broadcast layer. So there's no need to talk to the internet, but what you're getting over the very thin layer of L-band coverage to a degree is this the correction for the orbits and clocks. So we can get some correction. We can get down to maybe 1 meter to 2 meters at that point. But there's only so much bandwidth. We can only send so much data over the air to the receiver. So again, depending on your application, you will choose something, one of these two potentially. Then it's consideration around time. So we can wait for a long time with the PPP services because we have to wait, get all the satellite data down, which comes slowly. And when we've got it over a period of time, we can work out where we are between 10, 20, maybe a few more centimeters. But it takes a bit of time. So if I'm now a self-driving car coming out of a parking lot with a customer on board, this isn't really an option because the nav needs to kick in straight away, as an example. And over here, this is instant. And also the accuracy is millimeter in some instances if you want it to be. So it's, there's more cost involved here for millimeter to centimeter level, far less cost and often free for the service perspective from the PPP point of view, but it doesn't tick all the use cases. So you'll see a number of vendors now coming to market, what we call the best of both worlds, the PPP RTK, which effectively is going to get you not to the 1 centimeter, because the cost of going from 3 to 6 centimeters accuracy, rather than just the 1, the cost is much, much lower. And the ability to deploy it is much easier, and the operational cost for the end customer is negligible. So this is really the right type of service if you want to build a product that could work anywhere in the world, or at least anywhere across the continent, where you don't need any setup or any overhead. And there's kind of some examples of these options really. There's 4 kind of RTK perspective. You'll see these 2 models as I mentioned. You'll see this classical setup where we set up our base station, it works out where it is, and it will then locally communicate to around a 20 kilometer radius an exact position, which is great for, as I say, certain industries. But if you are building a consumer product like a robotic lawnmower or robotic snowblowers I've seen in the US, no one's going to set this up in their garden. You just need to ship them a snowblower that's going to automate and do its thing. So this isn't really the best option for that scenario. But then there's the option of what we call these virtual reference station networks, and there's a few in the UK that operate in most farming areas, but not in North Wales, for example. So again, if you've got applications where you need to get that precision, and you're considering one of these kind of regionally operated virtual reference station networks, then always check their coverage, number one, and then also consider the fact this is going to be using cellular data to communicate non-stop to the internet to receive this information at 4 to 6 kilobits a second. So again, there's an operational cost that's often hidden, that people go, man, I didn't realize the amount of data I'm using for this thing, because they might have developed the whole application from a different perspective than knowing about the intricacies of this technology. And then the PPP, again, it's courtesy of one of our partners, Callian. This is, as I say, where the information, the truth systems are on the ground. Some of that data is being sent up to the satellites, and they beam down an element of the correction. So that's a useful service for, again, maybe farming and these applications that are in the middle of nowhere. Certainly maritime. That's where you'll get more accuracy. But again, often ships don't need to know exactly where they are, for example. But gives you an idea of some of those options. And then another option is this PPP RTK, which is, of course, U-blox is one of the vendors. That's why we're here talking about that. But effectively, this is where we've set up our own reference stations around the world. They are all receiving all the satellite information from space across, multiple, every 100 kilometers or so. We've got this patchwork of these reference stations, and all that data we're feeding into the internet, where we're pushing it through our algorithms to correct the data. And so we were only talking this morning about a customer who's got a bit of a challenge at the moment because some of their maps have kind of gone out of sync over time, over 100 years. And it's partly because they're not using up-to-date, algorithmically driven corrections. They're trying to calculate the corrections from a fixed map from like 100 years ago. But since about 100 years ago, I think the Earth has gone 80 centimeters to the west. The actual plates move. So that's the problem. So these are all the subtle things that are unknown until you start talking to people that really understand the depths of these, of which I'm not one, by the way, just to say. We've got some people at the back who know what they're doing there. But the point is, the Earth's constantly moving. Even for drones, there's earth waves that are coming up and going down. So again, for drone delivery, at the very precise point you're going to be flying your drone in to deliver a burger, the vertical accuracy is really important to know, rather than crashing the top of your drone off. So subtle things that make a big difference that often aren't discovered until later in a project when you're trying to get the navigation component of your autonomous vehicle development organized. And then again, this is our stats from our own data, but they're common to some of these services you'll come across. If you're not correcting the data, then look, we've got a 40 to 70 centimeter kind of, I think I'm here. It's kind of doing this all the time. Whereas if you then talk to the internet, say, no, we know exactly where you are, here's the corrected data, you then get the pinpoint on the map. But you need to be talking to the internet to receive that stream of correction data. So, if you can imagine, we've now got some, this kind of an understanding of what's going on here. And as I say, we're kind of blatantly promoting one of our partners here. There's a number of them, but they're building smart antennas, which helps solve a lot of what I've just explained. Hopefully you'll never have to scratch your head and wonder what's going on, because there's companies out there who are packaging all this into super optimized, properly tuned smart antennas. So another part of the whole project is the antenna. So we were talking again this morning to someone who are building different devices for people with eyesight impairment, so effectively virtual guide dogs, and they're coming in different formats. There's rolling options, there's things you can wear that give you haptics, and again, some of the challenges these guys are facing in their developments is where do you put the antenna, because you do need some concept of seeing the sky. We've had other customers building worker safety applications when they've got body cams with GNSS in and they're not getting the accuracy. All the tech's working correctly, the antenna is just at the wrong angle completely. So that causes huge problems. So again, if you want to bypass these problems, I'd head to someone who has a smart antenna where all of this is bundled up. And effectively, some of these challenges that we get, such as even the signal going from the receiver or from the antenna to the receiver, can be messed with inside the device. As you might work, many of you probably work with RF and know this, but with satellite specifically, it can cause chaos in the project, often not being able to even figure out where the problem is until we send it to one of our partners' labs, where they can tell you, the 5 millimeters you're hopping that data across from the receiver or the antenna to the receiver, it's breaking for some reason. So again, the likes of Callian and others are building these products to overcome almost like the final hurdle when you get to your project where you think, man, we've done it, we've worked out this technology, and finally it's not quite getting there. A good way to even start the test, even if you're going to end up with your own housed or your own antenna design, starting with a smart antenna to start with, is not a bad shout to make sure you've got the basics all in place. And then something that's changing in all of those early examples I gave you from those businesses, the way in which these commercial services are sold. Another quite important factor that we would recommend you kind of look at up front. What I mean by that is you can get a centimetre level service for a couple of $1,000s a year per device, upfront license. So now we've got a bit of a capex challenge especially for a startup. It's just not viable. But if now I've got a delivery robot that's only going to work, Juha's from Finland, my colleague here, I doubt they'll be working in the winter much. So if you've got a delivery robot that's going to work for 6 months of the year in the summer, you don't want to be paying for the whole year. So again, check with these vendors to see if there's commercial plans that charge for the usage. So again, something we've done at U-blox is kind of almost copy what Amazon do, which is we only charge companies for what they use, as opposed to a traditional method with the more traditional RTK technologies where it's upfront, and it's going to work, it's going to be good, but is it the commercially right choice for what you require? So again, having these different types of options where individual device can just consume and they just pay for what you pay for what they consume, or you can have fleets of devices that just all share a pool of hours or minutes for the consumption of their products. And again, as I say, the correction service market is a commercial market, but it's very broad in terms of the costs involved. So again, always check up. Once you start putting technologies on board your developments, just double check in advance what the price will be in 6 months, a year's time when you actually come to commercialize them. Because you don't want to be necessarily redesigning chips out or chips in or different services in and out because of these types of early considerations that were needed. So that's a bit of sound advice, if you like, from some of the customers we've been working with. And then I guess the key point I'm trying to make to you is it's quite a complicated area. Like everything in technology, it's all complicated. It's the physics involved in the satellite aspect are quite extraordinary in some respects. And so if it's an important feature within your design of any autonomous thing, then looking for these finished products, turnkey solutions from the get-go, they might fit. If they don't, longer term, you design something yourselves. But if you can start with pre-packaged products first, so you've got that piece right, because the rest of the application is what you'll be working on. So as I say, with drone companies, they're worrying about the flight design and how these drones are going to lift payloads. That's their focus. That's what those engineers are really skilled in. They don't really care about the navigation, but no one likes these hidden kind of challenges that will arrive from the positioning component of that. So that's kind of our message today from passing on some knowledge from customers, if that's useful. And if I keep pointing the thing at the right place, that's it. Thank you.
Thank you so much.